You know that feeling. You're trying to build the next great search system. Maybe for your company. Maybe you're just a researcher staring at, like, a mountain of data.
Oh yeah, been there.
You need it lightning fast, super smart, got to handle all the information out there. So you start with the basics, right? You train on single vector retrieval.
Makes sense. Start simple.
And at first, it's pretty great. It's fast. It uses MPIS maximum inner product search, which is, super optimized. But then inevitably,
Right.
you hit this frustrating performance ceiling. You're thinking, okay, what's next? This thing's going to crush me.
Right. It just doesn't scale or perform well enough on complex queries.
So then you hear about these multi-vector models like ColBERT. Everyone's saying they're supposed to crush information retrieval benchmarks, with their fancy late interaction, deep semantic understanding. Sounds like the dream.
The silver bullet.
But then reality hits you like a ton of bricks. Retrieval costs skyrocket. That chamfer similarity they use, ugh.
It's a computational nightmare. Seriously expensive.
You're pulling your hair out trying to scale this thing because your current system is definitely going to crash and burn otherwise.
It feels impossible sometimes.
Then someone tries to patch it up, right? They build these elaborate multi-stage pipelines, like PLED, to try and make it work.
Ah, yes, the four-stage pipeline approach.
But it's complex, it's finicky, super parameter sensitive, and honestly, it's still just slow.
Yeah, reproducibility studies have even highlighted how tricky those pipelines are. Finicky is a good word for it.
So you're back to square one, staring at that mountain of data, slow, expensive solution, wondering if there's any other way.
And that's exactly when the big question hits you, right? What if? What if multi-vector search could be single-vector search?
Like, could you build a bridge?
Exactly. What if you could build a practical bridge between the immense power of those multi-vector representations and the lightning speed of single-vector systems?
Okay, I'm listening.
That's precisely what a groundbreaking new approach called MUVERA does. And it does it with something they call Fixed Dimensional Encodings, or FDEs.
FDEs.
It cleverly squeezes those complex multi-vector queries in documents into single fixed-dimensional vectors. One vector per item.
So it simplifies things down.
Massively. And here's where it gets truly fascinating. When you take the dot product of these new FDEs, just a simple multiplication, it closely approximates the original complex chamfer similarity.
Wow. Okay, so it mimics the complex calculation, but way faster.
Precisely. And this isn't just a hopeful hack like, oh, maybe this works. It's mathematically proven to be an epsilon approximation. It provides the first theoretical guarantee for this kind of problem.
A theoretical guarantee, that's huge.
It is. No more guessing, no more relying on those finicky heuristics. It's a provably sound approach.
So what does this all mean for you, the listener? Our mission today is to unpack how MUVERA achieves this incredible feat, what it means for the future of information retrieval, and why it's such a profound step forward. We want to deliver that aha moment without getting totally bogged down in the dense research paper.
Yeah, let's break it down.
Because we're talking about getting the same recall, the same quality, while retrieving 2 to 5 times fewer candidates than those old single-vector heuristic methods.
Which saves a lot of computation later.
And when pitted against Play, the existing multi-vector champ, we see an average recall jump of 10% with a staggering 90% lower latency.
90%? That's massive.
Plus, you'll learn how they compress these FDEs by 32 times with hardly any quality loss. It's a significant leap forward. The core problem, why multi-vector search is a nightmare and why we need it. Okay, let's maybe step back a tiny bit and set the stage for modern information retrieval. For a long time, we were, pretty okay with simple keyword search.
Find the exact words, good enough for a while.
But as data just exploded and our questions got more nuanced, we needed something smarter. That's where neural embedding models came in. They really shifted how we think about search.
Fundamentally changed the game.
These models basically convert words, phrases, even whole documents into numbers vectors that capture semantic meaning. Not just keywords, but the idea behind the words.
Right, so similar concepts are close together in this vector space.
Now, within this world, there are two main players we need to understand. Single vector, SV, models, and multi-vector, or MV, models.
And each has its pros and cons, big trade-offs.
Exactly. Let's break those down.
Sure. So single vector models, like we touched on, each query or document gets just one embedding one single vector.
One vector to rule them all.
Kinda. And the huge advantage here is speed. You can use these highly optimized maximum inner product search, MIPS, algorithms. They find the closest vectors really, really fast.
Because it's just comparing one vector to another. Simple.
Super simple comparison. Think of it like comparing each document to your query as a single unified idea. Incredibly fast.
But limited, as we said, that performance ceiling.
Right, it can miss nuances. That's where multi-vector models come in, like the famous ColBERT model. Instead of one vector, they represent data points with multiple embeddings, often like one per token or significant word.
So a document isn't one idea, it's a collection of smaller ideas.
Exactly. And the benefits are clear. These models usually offer superior performance because they capture much finer-grained details, things a single vector might just average out and miss.
Okay, so better results, better understanding.
Yeah, better interpretability, too. You can see which parts match. And they tend to generalize better to new kinds of data.
Sounds great. What's the catch? There's always a catch.
The catch is massive computational expense, producing one embedding per token. Well, you can imagine, right? It increases the total number of embeddings in your data set by orders of magnitude.
Suddenly you have billions or trillions of vectors instead of millions.
Precisely. And the real bottleneck is how these models score similarity. They use that chamfer similarity, sometimes called maxim.
The nightmare we mentioned.
Nightmare. Imagine your query has, say, 10 key concepts represented by 10 vectors. The document might have hundreds or thousands. Chamfer similarity doesn't just compare averages. No. It meticulously finds the best possible match within the document's vectors for each one of your query's 10 vectors. Then it sums up those 10 best match scores.
Wow. Okay, that sounds thorough. And slow.
Incredibly thorough for understanding nuance, but incredibly slow and complex to calculate, especially at scale. Brute force chamfer scoring is just computationally prohibitive for any decent-sized data set. You just can't do it directly for search.
Okay, so if multivector is so much better qualitatively but also way slower, how have systems actually tried to make it work until MUVERA came along? There must have been attempts, right? Like PLAID?
Yeah, absolutely. The most common approach has been what the MUVERA paper calls the single vector SV heuristic. Systems like ColBERT TV2 and PLAID, which is, a leading engine for this stuff, use this.
The SV heuristic? How does that work?
What they do is essentially query a fast MIPS index, but they do it for every single query token independently.
Wait, so if my query has 10 words or 10 tokens?
It's basically 10 separate fast MIPS queries, one for each token.
Huh. Okay, that sounds manageable-ish.
But this SV heuristic has a lot of problems. First, it forces you to over-retrieve candidates. Massively.
Why?
Because multiple query tokens might all point to the same document as being relevant, right? So you end up retrieving the same document maybe 5 times if 5 of your query tokens match it well.
Ah, so lots of duplicates.
Tons of duplicates. You have to retrieve this huge list of candidates, maybe thousands, just to get a few hundred unique ones after deduplication.
Which is computationally expensive just for the retrieval part, even before scoring.
Exactly. And then there's PLAID itself. It tries to manage this with its complex 4-stage pipeline to progressively filter and re-rank these candidates.
The Rube Goldberg machine.
Pretty much.
Oh.
While it's optimized, studies have shown these multi-stage pipelines are, and I quote, complex, finicky, and parameter sensitive.
Meaning hard to set up and tune.
Very hard. Difficult to get right. Difficult to reproduce results. It's just complicated. Too complicated. 2. MUVERA's elegant solution, the bridge to speed and accuracy.
Okay, right. So if the current solutions like PLAID are complex, slow, finicky, MUVERA comes in with this, it sounds almost deceptively simple. What if you could take that powerful but nightmarish multi-vector similarity and just turn it into a single vector problem?
It does sound a bit like magic, doesn't it? Too good to be true.
Yeah, but that's exactly MUVERA's core breakthrough. It manages to reduce this multi-vector similarity search down to a standard single-vector similarity search. And it does this using those clever things called Fixed Dimensional Encodings, FDEs.
FDEs, that's the key.
This is the bridge we were talking about, because once you have single vectors, you can suddenly use all those highly optimized off-the-shelf MIPS solvers like DiskScan, tools that are already super fast and efficient for traditional single-vector search.
Exactly. You leverage decades of optimization work on emails. It's a huge shortcut.
So how does it work? What are FDEs really? How do they build this bridge?
Okay, so FDEs are single fixed dimensional vectors. One for the query, one for the document. The absolute genius part is that when you calculate the inner product or dot product of the query FDE and the document FDE, which is a really simple, fast calculation.
Just multiply and add.
Right. That simple calculation approximates the original complex, slow, multivector chamfer similarity score.
So you get the benefit of chamfer's fine-grained matching, but with the speed of a simple dot product.
That's the core idea. It makes efficient MIPS possible for multi-vector models. It's absolutely crucial.
That's clever.
It's also worth noting quickly that they generate the FDEs slightly differently for queries and documents. It's called asymmetric generation. It just helps optimize the approximation for how search actually works in practice.
Makes sense. So how are these FDEs actually made? Is it super complex?
The underlying math has some depth, but the process itself is conceptually quite elegant. You don't need to be a math whiz to get the gist. Let's break it down into a few steps.
Okay, lay it on me.
1. Smart grouping, or space partitioning. First, MUVERA takes all those little individual vectors from the original multi-vector representation, remember, maybe one per token.
Yeah, lots of them.
And it intelligently groups similar ones together. It divides the whole vector space into a predefined number of bins or clusters, let's say B bins. The goal is to make sure vectors that are close together semantically are likely to land in the same bin.
Like sorting similar ideas onto the same shelf.
Exactly. They use a method called SimHash for this, which is efficient and robust. It doesn't need to pre-analyze all your data, which is a plus. It's like setting up predefined zones.
Okay, grouped the vectors. Step 2.
2. Summarizing each group, block vectors. Once grouped, MUVERA creates a small summary vector for each of the B bins. This is called block vector.
A summary for each bin.
Yep. For queries, it typically sums up all the query vectors that landed in that bin. For documents, it usually calculates the average or centroid of all the document vectors in that bin. This is a key step, condensing lots of fine-grained info into a manageable block while still capturing the essence of that group.
So now you have B summary blocks instead of potentially thousands of tiny vectors.
Right. Much more manageable. 3. Compacting and refining, projections and repetitions. To make things even more efficient and robust, these B block vectors might get compacted slightly using something called random linear projections. Think of it like making a sketch captures the key features but smaller.
Okay, shrink them down a bit.
Then, crucially, the entire process, grouping and summarizing, is repeated multiple times, say R times, using different random perspectives each time.
Why repeat it?
It's like getting multiple opinions. This ensemble approach dramatically boosts the accuracy and reliability of the final FDE. It smooths out any randomness from a single run.
Ah, clever. Safety in numbers.
Exactly. Finally, all these compacted, summarized blocks from all the R repetitions are just stitched together, concatenated end-to-end.
Concatenated.
So if you have B bins, and each block is compacted to the dimension dproj, and you repeat R times, your final FDE dimension is B times dproj times R. That forms the single, final, fixed dimensional encoding vector for the entire query or document.
Got it. So you end up with one vector that cleverly encodes information from all the original little vectors, organized by similarity and refined through repetition.
You got it. And there are a couple of other neat practical details, like how these smartly handle bins that might end up empty for a document, ensuring the approximation stays accurate. And an optional final projection step can even squeeze out a tiny bit more performance.
Okay, wow, that's a sophisticated dance behind the scenes to create these compact FDEs. But like we said, this sounds like elegant theory. What kind of guarantees does it offer? Does this sophisticated math actually hold up in the messy real world? 3. The proof is in the pudding. Theoretical guarantees and real-world performance.
It absolutely does hold up, and this is where MUVERA really distinguishes itself. One of its most significant contributions isn't just the method, but the strong theoretical guarantees that come with it.
Okay, the guarantees. What are they?
Remember we said the FDE dot product approximates chamfer similarity? Well, it's proven to be an epsilon additive approximation.
Epsilon additive. What does that mean for me, practically?
It means the score you get from the fast FDE dot product is mathematically guaranteed to be very, very close to the true slow chamfer similarity score. The difference is bounded by a small, predictable margin of error called epsilon.
So it's not just a guess, it's provably close.
Exactly. This is a huge leap because it gives you a principled, provable way to tackle this complex multi-vector problem. You're not just relying on heuristics that might work sometimes but fail others. You know how good your approximation is.
That's confidence-inspiring.
There's also another neat property. It's a one-sided estimator. The way FDEs are constructed means they never overestimate the true chamfer similarity.
Never overestimate. Why is that good?
It means the score you get is always less than or equal to the true score. It gives you a reliable lower bound, which can be very useful in ranking and retrieval systems. You're not accidentally promoting something that shouldn't be there based on an inflated score.
Okay, solid guarantees. What about speed?
That's the other major theoretical result. MUVERA is the first algorithm with provable guarantees for chamfer similarity search with strictly faster than brute force runtime. And it speed scales incredibly well. The time it takes depends logarithmically on the size of the data set.
Logarithmically? That's amazing for large data sets.
It's exactly what you want for web-scale search. It means even if your data set doubles, the search time barely increases. This is a game changer for making these powerful models practical at scale.
Okay, the theory's strong. But here's where the rubber meets the road, right? The numbers. How does this theoretical elegance translate into actual practical gains we can see and use?
Right, let's look at the experiments. The results are really quite compelling. MUVERA was tested rigorously on 6 diverse BEIR datasets. It's a standard benchmark suite for information retrieval. Includes big ones like MS Marco and others like HotPotQA, NQ, Quora, Sidox, Arguana. They cover different sizes, different document lengths, different query types. A really good test bed.
Okay, diverse data sets. What embeddings did they use?
They used ColBERT TV2 embeddings, which are standard 128-dimensional multivector embeddings, and they tested FDEs with dimensions ranging from around 1,000 up to 20,000.
So what did they find? Let's start with the FDE quality itself.
Yeah, they did an offline evaluation first, basically checking how good are these FDEs as a proxy for the real chamfer similarity.
Do they actually capture the right ranking?
Pretty much. And they found that FDE recall quality improves dependably as the dimension dFDE increases, which is great. Means you have a clear trade-off, need more accuracy, use a slightly bigger FDE, need to save space, use a smaller one, predictable performance.
And what helped quality most?
Increasing the number of repetitions, R, the FDE generation process, had the most significant impact. That ensemble approach really pays off.
Okay, good to know. How did FDEs compare to that old SV heuristic used by Plaid?
This was a key comparison. The results showed FDEs are a much more effective proxy for multivector similarity. Way better.
How much better?
For example, on MS Marco, to achieve the same recall level, say 80%, MUVERA's FDEs needed to retrieve only about 60 candidates per query on average.
Okay, 60 candidates.
The old single-vector heuristic. It needed around 300 deduplicated candidates, which meant retrieving maybe 1,200 or more initially before removing duplicates.
Wow, so 60 versus 300 unique candidates, that's 5x fewer.
Exactly. It dramatically reduces the amount of work the expensive re-ranking stage has to do later. Much more efficient filtering.
And was the process stable, since it uses randomness?
Remarkably stable. Despite the randomization involved in creating FDEs, the variance in recall was essentially negligible. Tiny standard deviations, very consistent results.
Okay, offline looks great. What about putting it all together, the online end-to-end system?
Right, this is the real test. How does it perform in a production-like setup?
What did they use for the MIPS part?
They used DISCAN, which is a state-of-the-art graph-based approximate nearest neighbor search algorithm. It's known for being very fast and memory efficient, especially with SSDs.
Makes sense. Use the best tool for the job. Any other optimizations?
Yes, they use that ball carving optimization we mentioned briefly. It speeds up the re-ranking stage.
How does that work again?
It basically clusters the query embeddings, those little vectors representing the query's ideas, and replaces groups of similar query embeddings with their sum, or centroid. So instead of calculating chamfer using maybe 30 query vectors, you use maybe 5 or 6 theme vectors.
Ah, simplifies the query side for the expensive part.
Exactly. It provides non-trivial efficiency gains. They saw about a 20-25% improvement in queries per second, QPS, with negligible quality loss. It reduced the number of effective query embeddings by about 5.4 times.
Nice gain. What about memory? FDEs sound potentially large.
That's where product quantization PQ comes in. This is huge for practicality. PQ is a vector compression technique. Yeah. They showed that using PQ, they could achieve 32x compression on the FDEs. For instance, a learned 240-dimensional FDE could be stored in just 1,280 bytes. Tiny.
32x compression, does that hurt quality?
Surprisingly little. And it has a massive benefit for speed, too. Because the vectors are smaller, they fit better in memory caches. PQ actually boosted queries per second by up to 20x in some cases, with minimal loss in end-to-end recall.
Wow, so PQ makes it smaller and faster. Win-win.
Big win-win. Okay, so now the final showdown. Comparison to Plaid end-to-end.
MUVERA versus the incumbent.
Across the 6 BEI datasets, on average, MUVERA achieved 10% higher recall with 90% lower latency.
10% better recall and 90% faster.
It's a massive improvement. MUVERA delivered significantly better latency on 5 out of 6 BER datasets.
Which was the exception?
MS Marco. Latency was similar there, possibly because Plaid, being developed heavily on MS Marco, is highly tuned for that specific dataset's characteristics.
Okay, but better on 5 out of 6 and much higher average recall.
Exactly. And perhaps just as importantly, the paper emphasizes that MUVERA achieves these consistently high recall and low latency results with minimal tuning effort.
None of that finicky parameter-sensitive stuff.
Right. It's designed to be more robust and easier to deploy out of the box. That's a huge practical advantage for developers. Less pain, better results. 4. Broader implications and future horizons.
So, okay, this is clearly a major step forward in retrieval technology. Let's zoom out. What does this all mean for you, the listener? For large language models that seem to be everywhere now, and just for the future of finding information, this feels significant.
It really is. Now, the authors are quite measured. They state that MUVERA simply improves the efficiency of retrieval without enabling any fundamentally new capabilities.
Meaning it doesn't let you do something brand new, it just makes existing advanced search much, much faster and more practical.
Precisely. But that efficiency gain is incredibly valuable. Think about large language models, LLMs. Retrieval is becoming absolutely crucial for LLMs.
For things like retrieval augmented generation, RAG.
Exactly. To keep them up to date with facts, to ground their answers in real information, to help them avoid making stuff up or hallucinating. Faster, better retrieval directly leads to better, more reliable LLMs.
So MUVERA makes advanced RAG much more feasible.
Absolutely. By making these powerful multi-vector embedding models practical and scalable, MUVERA directly supports the evolution and wider use of all sorts of AI technologies that rely on finding relevant information quickly. It provides the first principled method for multi-vector retrieval via a single vector proxy with theoretical guarantees. That's a landmark achievement in the research field.
A foundational piece, potentially.
Could be. Now, the authors are also good scientists and acknowledge limitations.
Right. What did they point out?
Well, as we mentioned, they didn't outperform Plaid on latency, specifically on MS Marco, suggesting Plaid might just be incredibly optimized for that one dataset.
Okay, fair enough. Anything else?
They also noted they didn't specifically study how the average number of embeddings per document, like very long versus very short documents, affects FDE retrieval quality. They flagged that as an interesting direction for future work.
Makes sense. You can't study everything at once.
Exactly. And for future directions, the path seems clear. Keep refining this FDE method. Given how efficient it already is, even small further optimizations could lead to even bigger gains down the line.
So MUVERA isn't necessarily the final word, but it's a huge leap onto a much more promising path.
I think that's a great way to put it. It's opened up a new, theoretically sound and practically effective avenue for tackling one of the biggest challenges in modern information retrieval. Outro.
Wow.
So,
This deep dive into MUVERA really drives home how a clever theoretical insight, that epsilon approximation idea, combined with some brilliant practical engineering, the FDE construction, the optimizations can build that essential bridge. A bridge between the power of multi-vector models and the speed we desperately need from single vector search.
it's truly impressive stuff, taking a computational nightmare and turning it into something manageable, even elegant.
It really is. It shows that sometimes the best way forward isn't just throwing more compute power at a problem, but fundamentally rethinking the representation.
Absolutely. And remember, it's not just a trick, right? It's a bridge built on solid theoretical ground, making state-of-the-art information retrieval finally scalable for everything, maybe forever, or at least for the foreseeable future.
A profound thought.
So, as you interact with AI tools, search engines, recommender systems every day, maybe take a second to consider the silent, lightning-fast processes humming away behind the scenes, processes like MUVERA. And maybe ask yourself, what other complex computational nightmares out there might just be waiting for someone to build the right kind of bridge by rethinking the data's fundamental representation?
That's a fantastic question to ponder. A great place to leave it. That's a wrap on our deep dive into MUVERA. We hope you feel a little more well-informed, maybe a bit inspired by the ingenious solutions researchers are building to wrangle the world's information and make AI smarter and faster for all of us. Thanks for joining us.